So good morning, everybody. Before giving the stage to Catalina from IN-CORE to present the inline quality control characterization service, I will first introduce the Teesmat project in just a few slides. So Catalina, please.
Yes, next.
Thank you. So Teesmat is a European project. It's an open innovation test bed for electrochemical energy storage materials. The idea behind Teesmat is that the European battery market is growing very fast, around 25% per year. And there is a strong need to develop a competitive battery value chain in Europe. It's one of the top priorities of the European Commission. For this competitive battery value chain, we need progress in the electrochemical energy storage, and this depends on characterization and understanding of all the basic processes. So we need advanced characterization techniques, and some of these techniques are developed by European research labs, but they are today underused by the companies. So next, please. Thanks. So Teesmat aims to provide an easier access to these advanced characterization techniques and services for the companies which work in the domain of electrochemical energy storage materials. And to this aim, Teesmat goals are in 3 steps. The first step is to set up the platform, the Open Innovation Testbed. And the second step is to demonstrate its added value by solving persistent and high impact industrial problems which are brought by industrial service users inside the consortium. And the third step is to ensure the OITB's growth, longevity, and of course financial sustainability, even after the end of the European project, to have a standalone platform. Thank you. So this project gathers 2 types of partners. The first type is service providers, such as IN-CORE we have today. And the 8 service providers of the project provide around 30 techniques, allowing to have insight into the chemistry, the morphology, the structure, the performance, and to perform also some modeling of the electrochemical and battery materials and components. The second type of partners is service users. So they are industrials which come with their user cases, their questions about their components or their materials. And the Teesmat platform has to bring the solutions to their questions thanks to the characterization technique. So there is a very special partner with CERMA Technology, who will be the single entry point after the end of the project. So the single entry point will be the contact for the customers and will dispatch these questions to the various characterization techniques. I also put the database because the database is really central in this project. It gathers and stores all the samples, all the tests, and all the results that are produced during the project, while ensuring a strict access control so that every partner of the consortium can have access only to the data that it is meant to see, and not to all the data. So CEA has 2 roles in this project. One, of course, is that CEA is the coordinator of the project. I am myself the coordinator. And it is also the responsible for the database. Thank you, Catalina. So to give you a quick view of the timeline of the project, we have, of course, the H2020 project, which is 44 months and which will end in a bit more than 1 year in August 2022. And there are two main phases in this project. The first one was to set up the organization, and the second one is to test the platform. So we are today in this second phase of testing the platform, and Cermatec has already taken the role of the single entry point. During this phase, we are looking for external partners who will not be part of the consortium, but who will either provide additional techniques, so there will be external service providers, or come with their industrial questions, and there will be external service users. So the external service users are typically future customers of the platform, and the external service provider may become future members of the commercial consortium, which can be a bit different from the consortium during the project.
Okay.
And so after August 2022, the platform will enter the commercial activity and will have to become financially sustainable.
Okay.
So I think I have finished, and I leave the stage to Catalina to explain you all the beautiful things that they are able to do at IN-CORE.
Thank you. Thank you, Fabian, for this introduction of the Teesmat project and of IN-CORE. Thank you also for inviting us for this webinar. I just wanted, if you see, okay, I think you see. Okay, so so in this webinar, I will be presenting our inline quality control solutions, traceability and the digitalization of the battery electrodes during all manufacturing steps. Yes, I forgot to say thank you all of people who are attending this webinar. Thank you for your time. So first of all, as Fabian did, I will just start with some slides of the context of the lithium-ion battery industry trends in Europe. And then I will go to just explain a little bit who we are, our role in the battery lithium-ion value chain, and the characterizations technique that I will be introducing later on in the presentation. I just have one slide in which I will just briefly explain our role in the Teesmat project, as this topic will be tackled in another webinar more in detail, or just for everybody to have this in mind. And then I will go further in detail of the characterizations techniques that we provide for the quality control of the electrodes during the manufacturing steps. So yes, this is simply another view of what just Fabian told us about, all of the booming industry in Europe, which will grow very fast and very big in the coming years. Not only about all electrical vehicles, but as well as other renewable energy industry. And Europe is now building all of these gigafactory projects in order to be able to provide all of the batteries that are going to be necessary. Yes. Okay. Now, in this booming market and industry, so IN-CORE System provides inline optical inspection solutions to control the quality of the electrodes during their manufacturing process. So here there's 3 different images of these vision inspection solutions installed. We have the cameras that the optical sensors that are fixed, while the foil, or the coated foil is continuously being manufactured and moves through the camera. And then we have the operator that has all of the real-time information regarding the quality of the electrodes. So we provide this, we manufacture, we design, and we install these vision inspection solutions according to the production context of each battery manufacturer, whatever the width of the foil, whatever the speed of the coating line, and the necessary resolution to detect the defects and do the geometrical control. We are French, by the way. We are located in Lyon, and our solutions are also deployed in other different industries. So here I just have slides to explain our role, our characterization techniques, where they are deployed and used in the battery value chain. So we are located in the at the electrode manufacturing level. So our solutions are deployed in the coating, in the calendaring, and the slitting line. I will go a little bit further in detail, but yeah, just to be clear that this is mainly where our technology and solutions are deployed. Okay, so I'm going to speak about our three main solutions. So here we have the inline inspections that allows to do all the dimensional and position control of the coating patterns. It allows to do the top and bottom alignment for the double side coating and to do all the defect detection. We have the linear track solution that allows to serialize each portion of the electrode while it is manufactured in order to provide all the necessary traceability from the manufacturing level up to the delivered battery module, and to have all this traceability and quality analysis connection since it's manufacturing, and then its performance following up when they're being used. And we have the digitalization techniques, which is quite an important and key parameter necessary for Europe in order to be able to provide high competitive and smart manufacturing for the batteries for the battery production. This digitalization allows to connect and to link all the characteristics of the electrodes while they're being produced to this unique code that I just spoke about, to link the quality and the traceability. This is just before starting to go more in detail about the solutions I just presented before. This is simply as one slide to just explain our role in the Teesmat project. So just as I said before, we do the quality control of the electrode. It means we do defect detection and we do some geometrical control. In the Teesmat project, we are working to develop a 3D technique to measure the height of the coating. This is more an informative slide, and as I said before, it will be tackled in another webinar, but mainly in this presentation I will tackle the inline solutions for 2D control of the coating electrodes. So now I just go more in detail about the linear vision solutions for the inline control. So just before starting, I thought of just giving this scheme of what the coating process is for that I will use throughout the presentation. So okay, we have the foil, copper or aluminium. We have the first coating for top for one side coating, the ovens for drying the coating, and then we go to the second one, so the bottom coating. Finally the ovens, and then we rewind again, and we can produce either continuous or intermittent coating. So now in this coating process, how are our solutions deployed and what do they do? What do we control and what do we monitor? So the linear vision solution, the characterization techniques provided by IN-CORE, they allow to do all the quality inspection for the defect detections, such as some of the examples in the images here. such as bubbles, lack of coating, scratches and strike, all the different defects in the coating area. And also, one is very important is the geometrical control in such as all the coating width and the position of the coating patterns. And when we have double side coating, then the alignment between the top and the bottom coating. Yes, and mainly this very important parameters that have a consequence and in the quality of the battery performance later on. So how do we inspect the surface quality and control the geometrical properties of the coating part? So mainly one of the most versatile means of control is the optical sensors. In the two images I have here, I show either one possibility of a standalone inspection station when we use line scan cameras, and above one images of a compact image sensor, which is also a sensor, but that can be placed very close to the product that needs to be inspected. These two possibilities allows one of the big challenges, that is to integrate it. How do we integrate these inspection systems into existing coating line where there's no where there's little available space? We need to have such as the image acquisition rate as well as the processing to be compatible with high-speed coating. It is necessary, according to the requirements of the industry, to have very high resolution, and we need to display all the real information to the operator in order to be able to do corrective actions in the coating process to be more efficient and avoid waste. When we have different inspection stations, we must merge all the information, and as well as broadcast this as the industry requires, and for the digitalization purposes, we must broadcast all this real-time information very fast to the cloud. So how do we adapt the solutions to every production context? So here, just simply have I have several sheets that allow to understand how this solution is modular and how do we adapt to the resolution, to the width, and to the speed. So we need the optical sensors, we need the adequate lighting, and according to the available space, according to the resolution necessary to detect the defects, we can add several line scan cameras to cover the web width. And obviously, if we need to inspect the bottom, this is the case, we add the line scan cameras. We synchronize the image acquisition with the web moving through an encoder. We have all with the necessary processing computers to process all the real time information, and to do all the measurements and detect the defects. And just as the image in my previous slide, now and more we can use compact sensors, CIS, which are very, very compact and can be very close to the product that needs to be inspected. There are some advantages and drawbacks of either using line scan cameras or CIS. The CIS, they are built in fixed sizes, so you have a fixed length, and sometimes the CIS adapts, suits well for the length of the electrode. And therefore they have also fixed resolution, and then if it suits, then it's perhaps a good sensor to be used. But sometimes resolution is not enough, or sometimes web width is not fixed for the CIS. So it is a balance between many different parameters that need to be studied in order to provide an adequate solution according, to the speed, the web width, the resolution, and also the price, because you can build a very super powerful inspection solution, but then you can have an over quality so something that goes beyond the requirements. And yes, this is the balance that the industry is looking for, and how our expertise can also provide recommendations which is the good system that suits. So if I use the same scheme as below of what the coating of our characterization techniques, how they can be used in the coating process. So we can have several inspection stations integrated in the coating line. We have, for example, station number 1, which is in the wet area of the coating of the first coating. Ovens are very large, long. So if this first inspection station allows to detect very fast the process drift, and so to be able to correct fastly this deviation, and then to avoid waste. Inspection number 2, you can also do defect detection and also do the geometrical control of the first coating. And again, you have inspection number 3, then to do the top and bottom alignment, and then inspection station number 4. This is the idea is to validate where these inspection stations can be integrated in order to provide the fast assistance to for the detection of the process drift, and to be able to do all this fast quality inspection. And of course, the broadcast and the communication of all these characteristics that has been measured to the cloud or to the MES infrastructure of the gigafactory or the factory. Okay, now I go to the second second solution or characterization technique, which is the linear track used for the traceability purpose. Okay, so here, in order to explain the big challenges of the traceability integration in battery production is, the idea is to serialize each portion, each individual electrode by engraving and marking one unique code. So the challenges is, okay, you have several processes in which you changes, you have material transformation that occur during the different processes. There are some questions about how does the code evolves during all these processes. Is it readable, or is the code destroyed? And how are you able to read this code through the different steps? We have in the different steps, you have first the chemistry, the mixing, then you have in the coating the manufacturing of the electrode, but then you have you have the cell assembly, and then the module battery pack. So you kind of have different codes that are associated to each individual electrode, then the cell, and then to the battery pack. Okay, and also there are big challenges in order to be able to mark this 2D code in the foil at the high speeds, at the right frequency between each code, and what is the information that you must code inside each individual code. So yes, there are still many big challenges. There are just an example of all of the information that is code, that is of the marking infrastructure of the code composition. You have, according either to the continuous or intermittent coding, you must define the frequency and of the code and where they should be located. you can decide. It is up also in discussions of the industry, or what are the needs of the industry, what is the information that must be quoted inside each code, and if it's also quality information, that it is linked of all the measured characteristics and how they are linked to this code and then broadcasted. So yes, this is also part of the definition of this traceability solution according to the requirements of the industry. I have just here, yes, how do you, another important part, that is, okay, you need first to be sure that you have unique codes that are engraved in the foil. You need to be sure that how to enhance or artificially read the code in case the code are not readable. As I said before, that you can have transformation or deformation of the code in the different processes. And how do you link all the measured characteristics of the electrodes to this unique code in order to have all the quality traceability available for the battery producers. So all of this is this solution that needs to be implemented. There are still many big challenges to tackle. There are other questions and still open points of what is the influence of this code in the later on in the performance of the battery. So again, once we have the codes, but then we go to the next, the electrode, sorry, and we go to the next steps, perhaps the code can remain in the waste area, so you don't have this impact. Or as well, we are studying different marking techniques, such as using UV wavelengths, but perhaps they don't damage a lot. They have less impact on the foil, and perhaps less influence or not influence at all in the performance of the electrode. Although this is still it's still very earlier for us to be able to answer the question of this, of how what is the impact on the battery performance. So yes, there are just different approaches, such as keeping the code on the waste, or using different techniques that have less impact. And this is what is being studying or getting more into detail with the battery producers. And as if I go to the digitalization part, so the association between the quality and the traceability, this is also, I take the same coating scheme that I just showed you before. Now I have, okay, the different inspection stations that I use to measure all the characteristics of the electrodes, do the defect detection and the geometrical control. And now we just have integrated, the linear track solution that will do the engraving of the 2D code, and following this code marking, you will have an inspection station to read the code and do all the quality of all the measurements, and then have this link between the 2D code and the quality. If I go perhaps to the next slide that shows a different view, yes, you have all the hardware infrastructure necessary to acquire the data, as well quality as traceability, and then you can not only link to the code or the characteristics that comes not only from the linear vision solution, but also from different sensors that can have measured different characteristics of the electrodes, and all of that is broadcasted to the MES infrastructure. Now, this is simply to show that in the different process steps of the manufacturing of the electrodes, such as calendaring and slitting, the solutions can be therefore integrated, because the technology is well suited for as long as the product is flat and it is moving through the lenses, then the technology is suitable. So it's well suitable as for the coating process, as well as for the calendaring and slitting, in which we can again measure some characteristics of the electrodes once they have been then pressed, and again read the code and associate the characteristics. And then when you go to the slitting, you will have the same possibility and same solution to keep both measured characterizations techniques. And once you go in a more large scale in the GIGAF, where you in the factories where you have several coating lines, several calendaring and slitting lines, then you can have the possibility to associate and have this digitalization information for all of your produced electrodes, and that will allow you as well to have all this quality information of your manufacturer, of your production, in order to improve and be able to be more efficient, to reduce the waste, to improve your yield, and have a more efficient manufacturing techniques. Again, so yes, there is this booming industry in Europe that it is being that is in construction, in deployment. Many different techniques are going to be necessary in order to be competitive, to be efficient, to be able to tackle all the European objectives, such as well in terms of productivity, as well of being more efficient, being more to produce more green batteries, and all of these characterizations technique will contribute to this European battery lithium-ion industry. And we believe digitalization is very important to have for the 4.0 smart factories. And yes, this is our technology and how it is deployed and used in the electrode manufacturing industry. And yes, I think this is all for from my side, and this is our contact information in case you have any questions. I thank you for your attention, and yes, I think I have finished.
Thank you very much, Catalina. Very, very nice and interesting presentation. I'm just having a look at the chat because there are some questions for you.
See the questions. Okay. I don't know how to see them.
Okay, if you want, I can read it for you.
Okay, yes, perhaps.
Okay, so the question is, how will the calibration and the verification of this vision system be done?
That is a very good question. Okay,
Hello. Yes, Christoph of IN-CORE. I'm more responsible for the image acquisition technical details. So the systems will be here calibrated at IN-CORE. We use dedicated calibration targets to basically compare optical resolution, or to calibrate the optical resolution versus physical resolution. Those targets will be then used again after the system is installed on site to check that nothing happened during transport, and as well left usually at client side or test site, in order that the system can be recalibrated if required. But as far as I know, the most systems, once they are installed stable, that can be used to verify again, but the system remains calibrated, because the installation, let's say, is sound enough, mechanically sound enough, so that there is nothing happening.
Yes. Okay, this next question about have you considered the use of R&D mapping to study the heat affected zone around the QR code when made with laser? No, so the question is no, we haven't considered this technique. Yes, there are still many open questions about the marking of the code in the foil. As I said before, there are now two approaches, either infrared or the UV. We know that UV has a less impact of this heat affected area. But still, we need to make some more trials and to make trials in perhaps in production context at the high speed of production speed, in order to validate as well the marking, the impact of this marking in the foil, and to be validated that they can be readable and not deformed in the different process. So there, yeah, still some validation of the different marking techniques. So how does the system detect different types of certain surface defects? Is it self-learning algorithm or a pre-written algorithm? Okay, so the way the system works is that the system learns. We teach what the system is teach of what a good electrode should look like. The first step is to just run one time. We do these learning procedures, in when the system learns what the normal production, the normal variability, the normal production variability thresholds should look like. So the system does not learn the defects, but in contrary, the system learns what how the good product should look like. And once the system had learned this, and you set up different parameters, the system detects all anomalies that are outside the tolerances that were defined. And by also setting up some rules, then the systems automatically detects this anomaly, and it is able to classify this anomaly according to the defect class that were set up. And there's some there is a smart algorithms to be able to enhance the classification in order to be automatically and detect the different anomalies according to the fixed the acquisition resolution that was that it is as it was designed the system. Okay, so thank you for a nice talk. What is the resolution of the detection? Okay, okay, yes. So we as from the different feedback that we've had according to the requirements of the industry, the acquisition resolution is 42. We can go down to 42 microns size of pixel. In the silent area, so in the coating area, because some defects have very high contrast, we can detect defects of the size of 1 pixel. In the edges, what we call the noisy area, then we need more than we need around 2 or 3 pixels to be able to detect detect the defects.
Okay. Catalina, there was another question before the one of Jakub. They were it almost at the same time.
Yes. Okay.
Yeah.
I will. I don't know what is the red rabbit sample, but here at the IN-CORE it is fine. Here it's possible to bring. Okay, now today it is possible to bring a A4 format sample of your electrode that we can check in our R&D lab, where we will acquire an image of the product in similar or by simulating what the industrial vision system would perform in industrial conditions, and we are able then to test this in-core system vision system for the product. From at the end of September, here in our locals, we're going to have advanced battery testing facility. There will be a drive room with calendaring machine and also a vision inspection system and the marking and the linear track marking system. And in this case, it will be possible to do some tests with real rolls, with the electrode in roll format that can be rewind, that can be unwind. It is possible to calendar, to press the, to do the calendaring process, or simply just to only do the vision, to do the inspection with the vision system installed in the calendaring calendaring machine. And this is yeah. Do you have already industry integrated with serial producers? And if yes, yes, the solutions already deployed in the history. They can go up to the 100 meter per minute speed in the coating lines. The vision systems, we have the sensors, and we have our own real-time processing computers that allow to process all the data when speed is high. And yes, I know it sounds very commercial, but it is possible to deal with very high speed as long as we have the processing computers installed, and the technology is there. It's just the balance of the industry requirements and of how complex is the vision solution, but it is possible, yes.
Okay, thank you, Catalina. Are there any other questions?
If people have any other question later, they can contact me directly if questions come after.
Okay, thank you very much, Catalina and Christoph, for your presentation today. Very nice to have you here.
Thank you for inviting us.
You're welcome. So I guess if there are no any other questions, we can just close the event for today.
Thank you.
And yeah, I would like to inform all the participants. We will continue with the Teesmat webinars in September, so after the summer break, and you will be invited as always via email. Thank you very much for joining us, and have a nice afternoon.
Thank you.
Thank you.
Thank you, Fabian. Thank you, everybody, for your time. Thank you.
Bye-bye.
Thank you.